Right, so I got cut off at the end of the last video. I can only go 15 minutes, and then the system cuts me off. So where were we? We were just nearing the end of this problem here. We have used one of the two Kirchhoff's rules to help us solve this circuit. We've used the sum of the potential differences across all of the circuit elements as we go around a closed loop. Okay, here I choose to start at A, go clockwise and end at A, calculate the potential differences across all circuit elements. The sum is equal to 0 because we start and end at the same point, so we must start and end at the same potential. So the sum of the potential differences must add up to be 0. Okay, we've guessed a direction for the current. We assumed it was clockwise. And when we look at this equation, right, we have the E's. I know E1 and E2. We have the R's. I know R1 and R2. I guess that 1 should be a 2 here. A little typo for the subscript. R2 is 10 ohms. I know that the sum of the potential differences is equal to 0. I have one unknown I. I solve this equation, right? That these four terms sum to be 0. I solve for I plug in E1, E2, R1, and R2. Again, R2, this is supposed to be R2 here, 10 ohms. Easy calculation, it's minus 0.333 amps. Okay, so 0.333 amps is definitely the current, the right current. The negative sign means, oh yeah, I guessed wrong. I said it was clockwise, it's actually counterclockwise. So make sure that if you work through a problem and you calculate a current and it's negative, make sure at the end of that solution, at the end of your solution, you say what the significance of the negative sign is. Or if you guessed right, make sure you say that you guessed right because it was positive. In this case, we guessed wrong deliberately. I knew the current was going to be probably flowing the other direction, but I just wanted to illustrate this point. Okay, so make sure that you don't miss that final step of your solution to a problem for circuits using Kirchhoff's rules. Okay, so what else do we have to say? Well, the current, yep, here it is. I say the current is actually going counterclockwise because it's negative. Let's see, what else can we do with this problem? You could ask, what is the power delivered by one of those two batteries? The answer is easy. The power is simply the current times the EMF. We saw a version of that equation a little bit earlier, but that's how you calculate how much power is delivered by any given battery. Okay, current times the EMF. So that'll be 4 watts. Note the units are watts because it's energy per unit time, a joule second, which is a watt. What is the power delivered by the 6-volt battery? Okay, this time it's there is a negative sign here. Negative sign. Why? Because if you look at the 6-volt battery in this picture up here, unlike what the figure says, the current is not flowing clockwise, it's flowing counterclockwise. It's flowing against the direction that the battery would normally want to be pushing the current. So as a result, the power calculation ends up with a negative sign. That's how it works out that you answer this question, how much power is delivered by the battery. What's the significance of the fact that when you do this calculation, you end up with negative 2 watts? Oh, it simply means the battery is not actually delivering energy, it's absorbing energy, okay, or absorbing power. And the battery, if the battery is designed to do this, will simply be recharging. Okay. So here's an exercise for you. I won't go through this in this screencast or in the notes, but you can verify that the power delivered by this 12 volt battery is equal to the power absorbed by the other circuit elements. Well, we have 2 watts being absorbed by the 6 volt battery. And you can also calculate the power associated with those 2 other resistors, right? That will be the rate at which energy is being produced in the form of heat in the resistors. If you sum the power absorbed by the 6 volt battery and the power created in the 2 resistors, it should sum to be not 12. It should sum to be 4 watts. Okay, which is the power delivered by the 12 volt battery. Okay, and all this is just simply saying that energy is conserved. Okay, however much energy in any given time is given by that 12 volt battery, that must be equal to the energy rate at which energy is being absorbed by the 6 volt battery and the rate at which heat is being produced in the resistors. Okay, let's continue and look at a somewhat more complicated circuit. This is a circuit with 3 distinct branches. We have a branch here, and we have a branch in the middle, and we have a branch in the bottom. A branch is identified as I can go along this path here between points B and C, and I don't come to any other junctions. So I go from junction B to junction C without crossing any other junctions. That means it's a single path, or a single branch. Likewise, B to C in here, that's another branch, no junctions in between. And B to E, F, and to C in that direction, another branch, no other junctions in between. Okay. So we have, first thing to do is we identify 3 separate branches, and we therefore put in 3 different currents. I'll label them I1. I'll guess that I1 is flowing left to right from B to C. I'll guess that I2, which is the current I'll put in this branch, is flowing in the direction indicated. So from B to E to F and then down to C. And then the third current in the bottom branch, I'll assume is flowing from C to D to A to B, okay, as indicated here. Right. So 3 branches, 3 currents. We need 3 equations to solve these 3 unknowns. Consider one of the junctions, C. Okay, so here's junction C. Look at the currents which are going in. I1 and I2 are going in. Look at the currents which are coming out, just one, I3. And the current rule is the sum of the currents going in, I1 plus I2, is equal to the sum of all the currents coming out of that junction. Well, there's just one, and that's I3. So there's one equation with the 3 unknowns, I1, I2, and I3. Now what we do is we apply, well, you could say, let's go to the other junction, do the same thing. Junction B, and look at the currents going in and the currents going out. What you're going to find is you will end up with the same equation. Okay? I'll leave that as an exercise for you. Give it a try. You're going to find you end up with the same equation. So it's not going to help. We need 2 other different equations, not a repeat of the same equation. So there are only 2 junctions, so I can't use the current rule anywhere else. Now I can use the voltage law, the voltage rule. And how are we going to do this? Let's go A, B, C, D, A. A, B, C, D, A. So this is a closed loop. Okay, we're going to take a walk around this loop, and we're going to choose to go clockwise. We don't have to. We could go counterclockwise if you wanted. You get the same equation as it turns out. So if we start from A and we go to B, nothing happens. And then as I go from B to C, 2 things happen. I cross a battery and the potential increases, low to high potential. Okay, so how much does it increase? Positive 10 volts. And then I cross a resistor. We're assuming the current is flowing to the right. Current flows downhill in potential. That means the current times the resistance gets a negative sign to indicate that the voltage difference, the potential decreases as we walk in that direction. And then I go from C to D, don't cross anything, and then I go from D back to A, and I cross one more circuit element, this resistor. And again, I3 is flowing from right to left. We're walking in the direction of the current. Current flows downhill. So I3 times resistance 2 ohms gets a negative sign because we're going from D to A. We're walking from D to A. So we're going with the current downhill in potential. Therefore, it gets a negative sign. And look, we have a second equation. Okay. Lastly, if we look for the, I can't quite fit this all at the same time. If we go E, F, B, E, so E, F, wait a minute, E, F, C, B, E, E, F, C, B, E. So we're going to walk around this loop. Okay, we can do that. So start at E, and the first thing that happens is I cross this battery, and I'm going from the high potential side to the low potential side, so the voltage is going to decrease. That's why it is negative 14 volts. Okay, so continuing our walk around this upper rectangular loop, I go from F to C, nothing happens. I go from C to B. Well, I'm crossing a resistor, so potential difference of I times R. Is it positive or is it negative? Look, the current I1 we guessed is flowing to the right. We're walking to the left. We're walking against the current. Current goes downhill, so we must be going uphill. So as a result, the potential difference is positive I1 times the resistance of 6 ohms. Okay. Next, we go across this battery. We're going from high potential to low potential, and it's going to be therefore negative and negative 10 volts. Finally, we have one more circuit element to cross. We're going from B back to our starting point E. And as we do that, we notice that we're going in the direction of the assumed direction of the current. We're walking with the current. Current flows downhill. We must have a negative potential difference. That's why we have negative current I2 times resistance of 4 ohms. There is your third of the three equations. Equation 1, 2, and 3. 3 linearly independent equations for 3 unknowns solve the equations. The rest is a math problem, kind of a standard high school math problem. 3 equations and 3 unknowns. Substitute equation 1 into equation 2. So replace I3 with I1 plus I2. Simplify that equation. I'll let you do the math yourself. You end up with equation 4. Okay. And then if you solve equations 3 and 4, now if you consider just equation 3 and 4, after having used equation 1, you see that we have 2 equations and 2 unknowns. Again, this is a high school math problem. I'll let you solve that part yourself. And when you do, you discover that I1 is 2 amps. Positive, that means you guessed the right direction. Negative 3 amps for I2, you guessed the wrong direction. It's actually pointing in the other direction. Finally, now with I1 and I2, we can solve for I3 using equation 1. Add them together. This one is negative. You end up with negative 1 amp. Again, the negative sign means the current is actually flowing in the opposite direction. Okay, and that pretty much summarizes everything you need to know. There are problems in your textbook. Look on page 475 for a good one.